in this video, I just wanted to go through a few exit problems. So I know we would typically do these extra practice problems in class. I think what might be a good idea is, as you look at this video in your notes that you're taking, attempt to complete this first example, and then work it out, and then watch my explanation, and then do the same thing with examples 2 and 3. Okay, so example 1, just kind of to recap everything that we've done here. Determine the intervals on which this function is concave up, concave down. So whenever you get the concavity question, that's where you're thinking what I've described as the second derivative analysis. And so we are going to go through the process of finding the second derivative, seeing where the second derivative is equal to 0 or undefined, creating that second derivative number line, testing points into that second derivative, and then drawing some conclusions from there. So our first derivative would be negative 18x squared plus 16x plus 6. And our second derivative would be negative 36x plus 16, just using basic power rule. So our second derivative is never undefined. We knew it wasn't going to be because we were working with a polynomial to start with, but it is equal to 0 at some point. And so if we solve this, we will get 36x equals 16. And divide both sides by 36, you get x equals 16 divided by 36. And you could take out a factor of 4, and so that's 4/9. So x equals 4/9 is the only key value that we're going to be putting on that second derivative number line. So I've got x equals 4/9, and again, we're going to label this f double prime of x, because we've always got to make sure that we label these number lines so that we know the correct place to plug in our representative values. So something to the left of 4/9 would be, I guess 0 would probably be the easiest thing there, and if you plug that into f double prime, you're going to get 0 plus 16, so that's positive. And then if you took something that was greater than 4/9, then you would get a negative. And so you could see here that we're concave up on the interval from negative infinity to 4/9. You're also concave down on the interval from 4/9 to infinity. And since the concavity is changing at 4/9, and 4/9 is a place where our function is defined, then x equals 4/9 is in fact a point of inflection. I didn't ask for it here, but that is a point of inflection. So that's a pretty basic one. With the polynomial, it's always going to be a little bit easier. So let's go through the same type of thing with a trigonometric function. And with this next one, even though I say find the points of inflection and discuss the concavity, it looks like a different question, but it's really the exact same thing. So once again, here, I'm going to do the second derivative analysis. Whenever you're looking for a point of inflection or you're asked to find the concavity, it's 100% the same. So we need to do our first derivative, and our first derivative is going to be negative 8 minus 2 times negative sine of x, or if I simplify that, the first derivative is negative 8 plus 2 sine of x, which makes our second derivative actually pretty simple second derivative to work with. It's going to be just, that goes away, so it's just going to be 2 cosine x. And so we need to see when this is undefined or when it's equal to 0, and we'll put those values on this number line. And I should have told you in this problem, I should say, because you're going to see this in Connect a lot, let's restrict our concavity, or let's restrict the function in this entire problem to the interval 0 to 2 pi. And so since we're restricting between 0 and 2 pi, then my number line, I don't want to draw with arrows on the end of it. My number line should be drawn like this. We've got 0 and 2 pi. And what are the places where the second derivative, where this 2 cosine of x is equal to 0? So cosine of an angle is the x coordinate. It's totally fine to lean on those unit circles that you guys have printed out. Hopefully those will help you going through some of this. So the cosine of an angle, cosine of what angle is equal to 0, and thinking that the cosine of an angle is the x-coordinate. So basically, what is the angle when the x-coordinate is 0? And that would be at pi over 2 and 3 pi over 2. So you'd say x equals pi over 2, x equals 3 pi over 2. Remember, label this the f double prime number line. So we're going to take some representative values and substitute them into our second derivative, which thankfully it's a pretty easy second derivative. And actually it's going to be easy to evaluate these values because we know that the cosine of angles in the first and fourth quadrants will always be positive. So that means that this is going to be positive and this is going to be positive because numerically that's the first quadrant and numerically that's the fourth quadrant. Also, we know that in between pi over 2 and 3 pi over 2, that cosine of those angles are negative. So you could see here that that we have a function that is going to be concave up on the intervals from 0 to pi over 2, as well as from 3 pi over 2 to 2 pi. And then we're concave down. We're concave down between pi over 2 and 3 pi over 2. And since the concavity changes at both of those places, then we would say we do have a point of inflection at both x equals pi over 2 and x equals 3 pi over 2. Okay, let's take a look at the third and final example here. So this last one, I said let's find all relative extrema for this function, and we're going to use the second derivative test if we can. And this is just a reminder that when you're using that second derivative test, what you're doing is you're first finding when the first derivative is equal to 0. So that would be negative 8x minus 32. I'm just setting that first derivative equal to 0. You get negative 8x equals 32, x equals negative 4. Then you take negative 4, and we're going to plug that value into the second derivative. Now the interesting thing is the second derivative is just negative 8. So no matter what you plug in to the second derivative, if you plug in negative 4, if you plug in any number whatsoever, you could pick your number, the second derivative is always going to be negative 8. So what does that tell you if the second derivative is always negative? Well, if your second derivative is always negative, that means your original function is concave down, right? So remember this from before. So when your second derivative is negative, your original function is concave down. And this would tell us that if x equals negative 4 was a place where the first derivative was equal to 0, then what type of relative extrema do we have at x equals negative 4? You can see that x equals negative 4 is a relative maximum. And we could describe it as negative 4 comma, you could figure out f of negative 4 and just by plugging negative 4 into the original function, then you've got your point. And in WebAssign, I'm pretty sure they're going to have you guys do that extra step where you're figuring out that y value. So that's a good summary of this section. Hopefully this gives you enough to complete the homework and everything. And just let me know if you have any questions as you're going through it.